Tell me, sir. Sir, now 1 hour கழிச்சு பேசுங்க சார். நான் ஒரு கெஸ்ட் லெக்சர் கொடுத்துட்டு இருக்கேன் சார். Sorry for the interruption. So this proof of capacity, again, it's similar to POS. That's not POS. Here also we are taking some power, computational power, but that computational power we are not taking directly the CPU. Instead, we are taking the capacity available in the hard disk, right? So here it will use what's called the plotting. So plot nothing but a high complexity hashes are taken here. That's called a sub-L hashes. So this hashing is a different mechanism here, which will be more complex. So and it's pre-computed and it will be stored in the hard drive. So hard disk it is already available, right? So these nodes they will create a nonce based on this hashing, and so it will store the nonce also, and whenever needed, it will take the nonce from this hard disk and it will use it, right? So if a particular node has more hard disk space, means he can store more nonce there and he can use it, right? So from that only it's using. So therefore, while during this mining process, it will generate what's called a deadline. That's how much time he need to complete that mining. That will be indicated. So minimum time to produce the next block, that will be indicated. So naturally, who is indicating the lesser time or who is having a lowest deadline, that will get the block, right? So here also the node which is having that doing the forging or block, that particular block he is creating, means he will get the reward, block reward, right? So out of the all these, it will have number of processes used for plotting, and nodes will store this in the hard disk, and from that it will use it, and therefore it will get the reward also. So it's highly efficient because we are not spending the CPU at that time. Everything is pre-computed and stored in the hard disk, so more energy efficient. And here, no rule for that one, right? If you are having some hard disk, you can get the chance. So anyone can become a miner. And this mining device can be used for other purposes also. So for multiple purposes, you can use it. And drawback here is, since it depends on this hard disk, it's less secure, and space also it needs more, right? And here, it will have what's called a grinding attack. So grinding attack means the same thing it will do again and again, right? So it will, for example, it has already created a nonce, but the defaulters they will get again the same thing, and it will they will take the same block, they will try to put the same block, and they will do the mining once again and again. They may be repeating. So that's a disadvantage. And this proof of capacity or POC is used in these networks, Filecoin and Bitcoin HD, Burstcoin, Storage. In these networks, they will be used. So next algorithm is, it's called a proof of participation or POP consensus algorithm. This as the name indicates, participation. Here it mainly focus on whether you are participating in the mining or not, right? So it's developed by the blockchain zoo, a company called Blockchain Zoo in 2019. Here it encourages all the nodes, right, to participate in the mining. So how much you are participating, that much chance you will get. That's why it's called a participation base, right? So here also will get a transaction fee, and coins also will be given as a reward. So anyone can apply to run a node, right? So this application automatically are accepted automatically based on the some rule. The rule is all nodes have equal chance, right? That's a main plus point here. Nobody can monopolize the network. Every node has a equal opportunity here, equal chance here to randomly get selected. So next block can be randomly selected for any node. If you are already participating, you will get more chance. So again and again, the users are encouraged to do that. So it's also energy efficient, and so main thing is here, all the participants will get almost equal rewards. So block creators can be different, so diversity will be there, and that's the main difference from POW and POS, right? Proof of work or proof of start, because anybody cannot take the entire mining process. Instead, all are given equal chance. So here, for getting accepted into the network, the participants has to wait for some time, right? For getting a reward, they have to wait for some time. So the another protocol is proof of ban. So now I will put on a video for this one.
Infinity nodes will implement the proof of burn mechanism, which by definition provides blockchain network validity by ensuring
Are you able to see the video? Okay, we'll proceed then. Sorry, 1 minute.
Infinity nodes will implement the proof of burn mechanism, which by definition provides blockchain network validity by ensuring that all participating nodes reach consensus. In Innovate's case, proof of burn will secure the network still further by forcing bad actors to think twice before attempting to carry out malicious activities. This is because SIN coins must be sent to a non-spendable address to initiate the burn process. Infinity nodes have an operational lifespan of 12 months, but must remain active for this entire duration to enable sustained network stability. Proof of burn will provide this stability for future use cases, such as incorruptible data storage, as a decreasing circulating supply will significantly lower sell pressure on investors and increase the value of their holdings, creating an all-round beneficial environment.
Yes, this proof of burn, it depends on that some work spent for getting the permission. Based on that only, it will get the permission and then it will be given the chance. So the next protocol is delayed proof of work. That is a DPOW. This what here it will do is it basically uses a Bitcoin blockchain only, right? So therefore, it will do one procedure called notarization. There is notarization means again, right, what we are getting from a notary public, a seal, like that. It's authorizing that, okay, this is the correct block, or it's having more security, and it's put into the Bitcoin blockchain so that nobody can modify it, right? So that's called notarized data. The data will be given to this notarized. Some nodes will do that. They are called notary nodes. So that notary nodes, by default, they will do this proof of work, and it's given. The data is changed, notarized data, and put into the Bitcoin. In addition to that, normal nodes also will be there. They will take the normal data, and this notarized data only will be put into the blockchain, right? So that's called a delayed proof of work, right? So here it will use the Bitcoin hash power only to enhance the security. So that here not only their own network, any third party, if they are joining this particular network, they can also use this one. And this was mainly designed by a project called a Komodo project. There's a system called Komodo ecosystem. In that they are using it. So for every transaction, one more layer of security is provided by this Bitcoin blockchain here, right? So suppose I want to change this transaction, Komodo transaction. First, I have to get the data from the Bitcoin blockchain only, right? That must be changed. After that only I can come here, right? So because internally it's stored in the Bitcoin only. So Bitcoin, we know that we cannot tamper the block. So therefore it is not possible. Like that, it's adding one more level of security. So how it is implemented is, it's implemented with the help of another Bitcoin platform called ZHash. In that code only it's integrated. And for doing this notarization and adding this block, notary block, this node, notary nodes, they will wait for an interval of 10 minutes, right? So why they are waiting for this 10 minutes is, so that the entire node or all the nodes in the block must, in the blockchain must validate that node, and everybody should agree, right? So that's why they are waiting for this 10 minutes. That's why it's called a delayed POW, right? And for this notary nodes, again, election can be, they will be selected based on election, community election. 64 notary nodes will be there, and they will write this hash. They take a snapshot of the entire blockchain, and it will be returned into the block. It will return as a block in the Bitcoin network. That's called a notarization. So main advantage here is security is more. So what are the protocols we have seen so far? Reply in the chat in the protocol seen so far. Please respond in the chat window. Okay. Madhumita answered first. POW, POS, proof of work, proof of stack, Sivashankari, madam. Okay, proof of burn, POC, proof of capacity. Okay, good. I am getting a response. So proof of work and proof of stack most commonly used, and then we have seen proof of capacity and proof of participation, where every node is encouraged to participate. Proof of capacity means based on the hardware capacity that norms is calculated and stored in the hard disk. That's a proof of capacity and a proof of participation. And then we have seen proof of burn, and the last one is delayed proof of work. Right? Very good. Congratulations for all the participants who responded. Good. So next one is proof of transaction. So proof of transaction, or it's called a POT. So this is used by a network called a TAU or a TAU. So this TAU means the active unit. That's a network like this, active unit, where this block time will be 1 minute. That's for every 1 minute a block will be generated. So here, as saying transaction, anyone can have a member of what's called a harvest club, right? It's again, it can be formed without the permission. I may not get permission anybody. Any node can have a set of nodes can have form a club like this, right? So for example, this will be the leader of that club, right? Harvest club, and A1 the address A1, A2 are coming under this one, and under A1 two more nodes A3 and A4, like that a group of transactions, sorry, a group of nodes can form a harvest club, right? So here all initial transaction will be automatically added into this harvest club for harvesting. I need not have any rule and all. So harvesting is similar to mining only. Here name is harvesting. So after this mining is over and that block will be added to network means, this leader will get the reward, right? So he will get the reward here, and once he gets the reward, what he will do is he will give a share to all his participants, right? Whoever is available here. For the intent, this A1 will give a share to A3 and A4. Like that, everything will be shared, right? So leader distributed this reward to the club members, and how much he will give is based on the volume of transaction up to 1 year, right? So far 1 year, how much transaction he has done, based on that he will be getting the reward, right? So and since it's based on volume of transaction, everyone will get interest, right? So I'm also getting some reward, so I also should involve, like that everybody doing some processing. So all the nodes here also, all the nodes are encouraged to participate. That's a main advantage here. Here I need not have any permission or any rule and all. Whatever the power we are having, computing power or whatever system I am having, I can participate. I should attach myself into one harvest club. That's all, right? Then I will be given permission, and the reward also I will get in turn back. So and this that's called proof of transaction. And this TAU or active unit mainly for phone mining. It's with the mobile phone itself I can do it, right? So here it's different from proof of work and proof of stack, right? And meaning that no hard rules, everyone is encouraged to do the mining process. The mining is here, it's called harvesting. The harvest club also, any number of clubs can be formed. For example, here A0 is one leader, no. Similarly, B0 is another leader of the harvest club, and their members are B1 and B2. Right, so they will involve also. They also will involve in mining and get reward. And B0 will distribute the reward to B1. B1 will distribute the reward to B2. Like that, the procedure will be there. Right, and another protocol is proof of elapse time. Now I will put a video for this. So here each node will be given a time, a waiting time, and for whoever initially it's assigned, and it's supported by Intel, right? So whoever is having less waiting time, they will be selected. So one by one, and they will get selected, and they will be given the power, and they have to attach themselves with that Intel. Some instruction set they are saying no, that they have to follow. And another protocol is called a proof of authority or POA. So now I will put the video for that.
Blockchain, the hype word of 2018. But do you know how a decentralized peer-to-peer system with no authoritative figure makes decisions? The answer lies in consensus mechanisms. There are various consensus mechanisms, but they all serve the same purpose: to ensure records are true and honest. The difference is the way the consensus is reached. Here, we will explore three types of consensus mechanisms. First, let's take a look at proof of work. In a proof of work system, transaction data is stored in blocks, validated by having people solve a complicated math problem attached to it. This is typically done by powerful computers and is known as mining. A reward in the form of a cryptocurrency is issued to the first miner who cracks the problem. Lost? Well, let's break it down. Imagine a group of treasure hunters trying to open a chest with a complicated lock attached to it. Figuring out the correct combination is tedious, but the first person to do so gets rewarded. Simply put, proof of work is a race to figure out the right combination on a treasure chest. Cryptocurrencies like Bitcoin and Ethereum use a proof of work mechanism. Next, we have proof of stake. Here, the creator of a new block, also known as a validator, is randomly chosen based on how much stake they commit to the network. Meaning to say, the higher the stake placed, the higher the chance to be selected as a validator. Let's apply this to the treasure chest scenario. Picture a group of treasure hunters vying for a chest. The chest is rewarded based on a lottery system. To participate, each hunter has to buy lottery tickets. The more each hunter buys, the higher the chance of winning. Blockchain protocols like Cardano's Ouroboros and EOS adopt the proof of stake consensus. Lastly, proof of authority. A modified form of proof of stake, here only approved parties selected based on their reputation can become validators. Let's revisit the treasure chest scenario. The group of treasure hunters form a union and pool their treasures. Based on their level of trustworthiness, a select few are appointed by the group to ensure the validity of the chest's content. IBM's Hyperledger Fabric and Ethereum's Coven testnet are some examples of blockchain systems that use proof of authority. Whilst traditional blockchain companies exist on a single consensus mechanism, some innovative ones are adopting multiple consensus protocols. Take Opet Foundation, for example, who is building a unique blockchain to store data collected on its tuition companion chatbot app by applying both proof of authority and proof of work protocols. Data such as students' academic, extracurricular, and personality profiling records are stored on the blockchain and potentially validated by a proof of authority framework powered by Hyperledger Fabric. Validators in this instance are reputable educational institutions or even national registrars and respective ministries of education. This helps ensure that all student data is trustworthy. But who will work for free? Proof of work consensus thus comes into play to reward validators who have performed work. With Hyperledger Fabric, each student record is secured with a private hash key owned by the student. The data can only be accessed when the students provide the unique key. This means student privacy is preserved and controlled by the student themselves. For example, when students apply to university via OPET's platform, they will provide the unique key of their records to the university. With that, the university will be able to access their latest academic records. Students will also be able to see if their records have been unlocked or at least considered for application. This boosts efficiency and transparency compared to traditional methods. By marrying the proof of work and proof of authority models, OPET Foundation's blockchain solution ensures privacy on students' data while incentivizing both educational institutions and students when they contribute to OPET's platform. With blockchains gaining popularity, it's only a matter of time before we see even more unique hybrid systems created.
Right, it's based on that trustworthiness, or some nodes may be given a chance, and they can combinedly from the group they can select, and they can be allowed to do the main. So it can be combined with other protocol also. So normally POW and POS also can be combined like that. Any combination, we can use it. And we have seen one application where university application students are encouraged with this combination of POW and POE. So far I have seen proof of transaction, where all are encouraged use by tau, and proof of elapse time is given, and based on that minimum time node will be selected, and proof of authority based on the trustness we can select it, right? So next one is next protocol is, it's called a proof of reputation, POR. So this proof POR, again the reputation, based on that only you'll be selecting, and this reputation is nothing but based on its asset it will be calculated. Asset, and similarly transaction, and how far they are participating in the consensus, based on that some value may be calculated, and new blocks will be generated by the node which is having the highest reputation. But for validation and confirm, for that other nodes can be used for they will put voting, and based on the voting we can select it. That's called a proof of reputation, and in one way it is a proof of authority only. It's basically it's using or it's based on proof of authority only, right? So nodes will be there. Among that, leader may be selected. So the reputation score is social activity time, how far they are involving in the calculation, everything will be taken into account. So normally within highest 5% who is available, they are put in what's called candidate pool, and from that candidate pool one may be selected. Randomly they can select. So, and these once it gets transaction is verified, means they will be put in their ledger, and similarly the reputation value, at the same time reputation value also increased for that particular node. So this here the nodes are randomly selected, and for verifying other nodes can be selected, and they can vote and they can verify. So here, since it's based on reputation, the transactions will be faster, and scalability also is more. And the main issue here is only for private and permission blockchain we can use it. Right? So here also 15% attack will be there, and that issue will be there, like proof of work. So they are used by GoChain, Benio1, and BitConch. These networks are using this protocol, proof of reputation. So, and the next one is delegated proof of stack, right? So I will put a video for this.
The delegated proof of stake, or DPoS for short, is is a cryptocurrency consensus algorithm that was developed in 2014 by American cryptocurrency entrepreneur and software developer Daniel Larimer. The DPoS system is maintained through an election process where coin holders vote for delegates who are then responsible for validating new blocks. It is considered by many to be a more efficient and democratic version of the preceding proof-of-stake algorithm, and they are both used as an alternative to the energy-intensive proof-of-work algorithm, such as the one used by Bitcoin. How does it work? The delegated proof-of-stake is designed as an implementation of digital democracy. Depending on the DPoS network consensus rules, a fixed amount of delegates from 21 to 101 are voted by the stakeholders of the network. These delegates, also known as witnesses, then validate transactions and get rewarded for adding blocks to the blockchain. Each stakeholder gets a number of votes proportional to the number of coins they own, or alternatively, they can choose to delegate their stake to another stakeholder on the network, who will then vote on their behalf. Under normal conditions, and depending on the implementation, delegates take turns producing a block usually every few seconds. Each delegate is scheduled for a specific time slot. Delegates who misbehave or constantly fail to produce a block will lose their reputation and will be quickly expelled and replaced by another delegate. Depending on the DPoS implementation, some systems may require delegates to deposit a certain amount of funds as a stake to show their commitment. These funds are kept in reserve and will get confiscated if the delegates act maliciously. In case of malicious or malfunctioning activity, the general rule is that the longer chain always wins. And anytime delegates notice a valid, strictly longer chain, they will switch from their current fork to the longer one. Delegated proof-of-stake can be implemented in numerous different ways. Compared to the proof-of-work algorithm, DPoS offers higher performance and a more energy-efficient solution by removing the intense mining competition, since ASICs are no longer needed to solve complex mathematical problems. This also promotes decentralization, since anyone can become a delegate, and no large mining pools are needed to validate the blocks. However, a sufficient decentralization can never be achieved, since the network cannot have an excessive amount of delegates without the risk of slowing down. The use of delegated proof-of-stake as consensus algorithm is growing among cryptocurrencies, but as the industry is moving fast, new algorithms will emerge in an attempt to further improve the current system. Stay tuned for more content, and don't forget to check out our other videos at Binance Academy.
So this delegated POS is an extension of POS. So based on the coin earned, the tokens will be generated, and with that they can do the voting, or they can give the voting to others also, so that they can vote in their on their own behalf. Like that, this voting will be done, and based on that, that miner will be selected. Right. So we have seen proof of transaction, proof of elapse time, proof of authority, and proof of reputation, and delegated proof of stake. Right. So on the last one, this we are already seeing in that video, hybrid POW and POS, the proof of work and proof of stake. So here, one example is this POW. They can create new blocks using their power, right? After these blocks are created, this POS miners will decide whether to confirm or not, right? So how they will confirm is, again, they will get the voting by stacking a portion of their tokens, and once they have some maximum number of token, they can vote for it. So now here, when they give the voting, total count is not selected. Instead, 5 votes is randomly selected, and therefore to check it, right? So if 3 of the 5 votes randomly we are collecting no, if 3 votes says that yes means, then that block will be added to the blockchain, right? So it's combination of both POW and POS, right? POW initial mining, and it's confirmed with the help of POS. And for that, 5 votes alone randomly selected. 3 saying okay means block will be added. Otherwise, it will not be added. And for reward also, it's given, it's distributed like this. POW miners will get 60%. And in the remaining amount, POS miners will get 30%. And remaining 10 is given for the that development work, right? Like that is given. So these are the various protocols, and these are mainly used for what's called a permissionless blockchain or Bitcoin, similar to Bitcoin. So similar to Bitcoin, a number of networks are there. All will be using a different protocol like this, right? So POS, POC, proof of capacity, proof of participation, proof of burn, delayed proof of work, and proof of transaction, proof of elapsed time, proof of authority, proof of reputation, the delegated proof of stack, hybrid POW, POS. And again, I have mentioned some one list only. Apart from that, again, more number of protocols are there, right? Each one will have its own advantage and disadvantage, right? So now that is for permissionless blockchain, it's over. Next, let us see similarly some protocols for permission blockchain. I think you would have heard for that Hyperledger, it will be using it will be using a practical Byzantine fault tolerance. Like that, here also some variations are there. I have taken some few algorithms only. So this, what's Byzantine fault? Byzantine fault means any node can behave maliciously, right? They can be Byzantine node means they will create either faulty or unethical also they may be there, right? So this is for permission blockchain, right? Every user must get a permission and then only they will be entering the networks. They will be given some ID and all, that's that. But after once entering into the network, whether they will behave properly or not, anybody don't know, right? At any time they may change, misbehave, or some nodes may behave properly all the time. All these combinations will be there. So here a consensus algorithm should focus on that also. That's why we are saying Byzantine fault tolerant and so on. So first one is what's called this Raft algorithm. So this Raft means replicated and fault tolerance. So as a measure of fault tolerance, a number of replication or copies also will be maintained, and this Byzantine fault also will be taken into account. So this is used in one of the protocol used by this another blockchain platform called R3 Coda. Coda also is under the open source platform for blockchain. They are using this Raft algorithm. So now let's see a video for this. So why I am putting video is they are clearly showing some this diagrammatically. It's more interesting.
Consensus algorithms are used to gain agreement between networks of nodes in distributed systems. A consensus algorithm must have these three following properties. Agreement, where every correct process must agree on the same value. Validity, the value agreed on must have been proposed by another process.
Is there anyone from coordinating team online? Resource person got disconnected. Excuse me, madam. Will you please unmute?
இதுவும் கட் ஆயிடுச்சோ
அதான்
இந்த வீடியோ போட்டோன்னே போயிருச்சோ
இப்போ ஒரு ஸ்லைட்
இப்ப வந்துச்சா
இப்போ
இது போட்டோன்னே போயிருக்கும் ரெப்ளிகேட் வச்சு. think I am audible now. This one algorithm is replicated and fault tolerance algorithm, which will take care of this Byzantine fault tolerance also. This is used in one of the network called R3 Coda. Coda is again an open source blockchain platform. In that we are using this Raft algorithm.
In this video, I will be talking about consensus algorithms. Consensus algorithms are used to gain agreement between networks of nodes in distributed systems. A consensus algorithm must have these three following properties. Agreement, where every correct process must agree on the same value. Validity, the value agreed on must have been proposed by another process. Termination, a value will eventually be decided by every correct process. Another important theorem for consensus algorithms is the CAP theorem. An algorithm cannot provide more than two of the three following properties: consistency, availability, and partition tolerance. There are different types of failures that a consensus algorithm might have to deal with. fail stop, network partition, fail recover, and Byzantine failure. Byzantine failure got its name from a computer science paper written in the 80s where the Byzantine generals problem is described. The problem describes 9 Byzantine generals who surround a city and they can only take the city if they attack at the same time. The generals can only communicate by sending flaky messengers who can get lost or caught. It is not known if one or more generals are traitors and will send messages to sabotage the loyal generals. There are many different consensus algorithms, but I will focus on the one called Raft. Raft stands for Replicated and Fault Tolerant. Raft does not use time, it uses terms instead. A term is an integer that starts at 0 and increments by 1 every time an election is held. Each term starts with an election represented by the red color. The time for the leader election should be a short fraction of the entire term. A node in the cluster can be in one of 3 states: follower, candidate, or leader. All of the nodes in the cluster start as identical followers that all have the potential to become a leader. Each follower has a random election timeout. To start an election, a follower times out, votes for itself, and sends out a vote request to the other followers. When a follower receives a vote request, it will increment its term. It will vote yes if it has not voted in the current term. Once a candidate has received the majority of the votes, it will become the leader. The leader will send out heartbeats to reset the follower's election timeout. These heartbeats come in intervals decided by the heartbeat timeout of the leader. The leader can also send append entries messages to the followers. These will also count as heartbeats and reset the election timeouts. Now let's imagine that a leader dies. A follower will not receive any heartbeats, and therefore its election will time out. It will become a candidate and vote for itself and request votes from the other followers. The leader is the only server that can accept data from the client. Followers will simply redirect to the last leader they heard from. To commit something to the log, the leader proposes append entries to the followers, and once a majority of followers has responded, the leader sends out a commit message. Once a value is on the majority of servers, it is considered committed. This allows the system to tolerate a minority failing, because there will always be an overlap in the majority.
So mainly here a leader and a follower will be there, and the follower has to get the, or they have to vote periodically, and they have to select the leader.
The going gets tough. Your skills will get you going. Stock
Sorry.
market skills have
So detailed algorithm we can refer, right? So and similarly in the Hyperledger fabric, they are using in this what's called a practical Byzantine fault tolerance. We'll show the video for this.
We've defined distributed systems, understood the definition of practice, and understood the various properties and limitations of these systems. We're now going to finish off by understanding all the possible areas in which these systems can fail, best summarized by the Byzantine generals problem. The Byzantine generals problem is a question of consensus. Allow me to tell you the story of the Byzantine generals laying siege to an enemy city. They've all surrounded the city, but there's a problem. Large physical barriers, like mountains and canyons, separate the generals. They can communicate only by sending messengers. In addition, they've not decided prior whether to attack the city or give up and retreat. Only after observing the enemy do they then decide on a common plan of action. Only an attack launched by all generals at once can successfully conquer the city. Having come this far, they send messages with their votes on how to proceed. Okay, you might ask, if they can send messages to one another, then what's the issue? They just need to collect enough information, right? So what's the problem? Well, the problem is that some generals may have been bribed. In exchange for their betrayal, they'll earn themselves a small fortune from the city. These traitor generals will send incorrect information to their peers in order to screw up the attack, preventing consensus. In addition, their messengers might get lost or corrupt their messages. The question which remains is, how do we achieve consensus, if we can at all? Spoiler alert, there is no solution in the presence of 1/3 or greater percentage potential trader generals. We call these potential trader generals Byzantine nodes, which may act maliciously or arbitrarily. In this image, there are two separate triangles. We consider scenarios with 3 generals and 1 trader, since the case is trivial with just 1 or 2 generals. Let's say the first general to send out a message is the commanding general, issuing commands, and the listening generals are the lieutenant generals. The node on the top of the triangle is commander, and the bottom 2 nodes are labeled Lieutenant 1 on the left and Lieutenant 2 on the right. The commander casts a vote for either attack or retreat, and the lieutenants record the vote. As you can see in the first triangle, Lieutenant 2 is shaded. This implies, according to our story, it's a traitor bribed by the enemy. In distributed systems terms, it's a Byzantine node. Either way, it's going to send incorrect information to its peers. Let's say the commander votes to attack, sending the message to both Lieutenant 1 and Lieutenant 2. Lieutenant 2, to mess things up, tells Lieutenant 1 that the commander said retreat. Lieutenant 1 now sees 2 different facts, only one of which can be true. The commander said attack, or the commander said retreat. In the second triangle, the commander is shaded instead. It tasks Lieutenant 1 to attack, but sends a conflicting message to Lieutenant 2, telling it to retreat. Lieutenant 2 dutifully reports to Lieutenant 1 that the commander said to retreat, but Lieutenant 1's problem remains. Notice that for Lieutenant 1, the information he's receiving is exactly the same as the previous scenario, even though the Byzantine node changed. The commander is telling it to attack, but the other lieutenant claims otherwise. Because these 2 situations are indistinguishable, the lieutenant cannot detect which node is malicious. In addition, because there is no clear majority value, Lieutenant 1 cannot decide on a value. With just 1 Byzantine node out of 3, it's impossible to achieve consensus. This example with 3 nodes extends to any general set of nodes attempting to come to consensus, meaning that consensus with the presence of 1/3 or greater Byzantine generals is impossible. If there were a solution that could tolerate more than 1/3 Byzantine nodes, we could use it to solve this much more simple scenario of 3 nodes. Since we know 3 nodes cannot come to consensus with 1 Byzantine node, we extend this to a general fraction. However, that doesn't mean it's not possible to make an algorithm for the remaining situations. Practical Byzantine fault tolerance, released in 1999 by Miguel Castro and Barbara Liskov, gives an algorithm to allow nodes to come to consensus with no more than 1/3 Byzantine nodes. This paper has inspired many iterations of Byzantine fault-tolerant algorithms, especially as research into blockchain consensus algorithms continues. Let's formalize the various types of faults within distributed systems. There are 2 main types of faults that are possible. While we can get into more detail between the types of faults, these 2 are the most fundamental to understand. The first type of fault is a fail-stop fault. During a fail-stop fault, the node can crash or not return values. Recall that a node's functionality includes sending, receiving, storing, and processing information. Early research into distributed consensus first aimed to solve these kinds of problems. This kind of failure may be temporary or indefinite, but it'll always be easier to handle than the second type of fault. A Byzantine fault, referring to the Byzantine general's problem, is a fault that refers to any arbitrary deviance from the protocol. In other words, not only might nodes stop replying or receiving information, but they also might send corrupted and or false information. You can note that Byzantine faults are a superset of fail-stop faults. The behavior of most attackers, such as that of bribe generals trying to hinder consensus, falls under this kind of fault. It is this type of fault that all public blockchains must protect against, since the participants in the blockchain network are unknown and unpredictable. Of course, the question after learning all this distributed system material is, how does this relate to blockchain fundamentals? Keep in mind the nature of blockchain. We've described it as many things: a technological solution to a social problem, the world's worst database, and a replacement for trusted third parties. But what is it in the context of distributed systems? Well, a blockchain is simply a data structure governed by a distributed system with an unbounded number of participants in the consensus process. And and an unknown number of Byzantine faults possible. In other words, it's the most adversarial environment possible. In spite of the incredibly low amount of restrictions possible, blockchain makes it possible for everyone to come to consensus. Clearly, the distribution of computational power and data storage represents the geographic distance between the generals. The nodes represent generals, and the traders represent faulty or malicious nodes. The possible drop packets or messages between nodes represent unreliable messengers, and coming to consensus on whether to include a block or valid chain of transaction history is the same as coming to agreement on whether to attack or retreat. It's the same concepts with different names.
So this practical Byzantine is nothing but what's used in this hyperledger. Now, another protocol is it's called a federated Byzantine agreement protocol. So it's used in another platform called the chain core platform.
Before diving into federated consensus, we're going to refresh ourselves with the definitions of all the terminology we've picked up thus far. Remember that a quorum in a distributed system is a set of nodes sufficient to reach agreement. In PBFT, that's over 2/3 of the voters. We refer to this as a Byzantine agreement within a BFT consensus algorithm. Let's say you're part of a decentralized distributed network, but you still can't choose which nodes to trust. How can you and your peers still come to consensus without relying on a central party to dictate the truth? This is where the concept of a federated Byzantine agreement comes in. Rather than relying on a central actor to choose quorums for us or to decide the truth for us, we can individually select who we trust using a quorum slice. This is a subset of a quorum that can convince a particular node, aka you, of agreement. Individual nodes can decide who to include within their quorum slice. Let's say you're the purple node, the leftmost of the set of 4 nodes. You believe a crayon to be red. The other nodes, who happen to be in your quorum slice, tell you that the crayon is actually green. Because you have decided to trust them, you change your opinion, instead coming to consensus with them that the crayon is in fact green. You then celebrate and rejoice the ability of trust to permeate through a decentralized network and allow you to reach consensus. Hooray. You might ask, what's the point of trusting these people? It seems arbitrary to me. Why not trust a central entity if we're handing out trust so freely? Keep in mind, these aren't the only nodes in the network. Let's say you only trust these 4 out of 1,000 nodes and you only want to listen to them. Of course, your follow-up question should be, if I only trust these 4 nodes out of thousands, how does the whole network reach consensus? This is where quorum intersections come in. By having overlapping sets of quorum slices, we can form a larger quorum and ensure consensus throughout the entire network. If all nodes share some individually selected trusted entities, then the whole network will still come to the same decisions without requiring a direct line of trust to any unknown node. You can trust popular entities with a lot of reputation, nodes which have been in the network for a while, or anyone else who you believe deserves the right to influence your decision making. In the scenario where these quorum slices don't line up, we get what are known as disjoint quorums, the pitfall of federated consensus. If this happens, then there is no way to guarantee that all actors will come to consensus. We've talked a lot about consensus in theory. How's about we go through an example? Let's say that Rusty, Derek, and I, Nadir, are trying to figure out what to get for lunch again. But this time, our friend group is ever expanding, meaning that new people will join us during the day. Since we're nice people, we're open to letting others join. But there's always trust issues when meeting new people for the first time. Rusty suggests pizza, his favorite dish, making the suggestion to Derek and myself. We two, however, know of a secret deal for $1 burgers today. Rusty, also a fan of burgers, and also acknowledging the value of the discount, cedes to our preference and decides on burgers as well. The 3 of us celebrate for coming to consensus.
Saroj notices our cheeriness and asks to join our friend group for lunch. However, he doesn't trust Rusty for whatever reason, perhaps because Rusty tried to get pizza on $1 burger day. Because of this, Derek and I decided to form a quorum slice with Saroj, meaning we all influence each other's decision making. Trust is beautiful, isn't it? Gloria, seeing how much our love has flourished, also wants to join us. However, she only trusts Rusty and Derek. Rusty and Derek also trust her, so they form a quorum slice as well. And ta-da! We now have 2 new overlapping quorum slices with Derek in the middle. Introducing the first quorum slice, there are a total of 3 quorum slices. The intersections are the most crucial parts, as those ensure that decisions made within individual quorums propagate to other parts of the network. Before diving into federated consensus,
so here a quorum will be maintained a certain number of nodes, and if quorum is not fully satisfied, subset will be taken and they will agree on that, and they can continue. And when more number of subset is there, they will be joined together and they will be combined together, and with that they will proceed, right? So these are nothing but some rules for coming into an agreement. So the next one is Paxos algorithm, which is actually in the earlier days, this is the oldest one. In the earlier days itself, for normal distributed system itself, they are using. For example, this Google company used this algorithm for their lock service, distributed lock service called Subby log distributed lock service. Similarly, Amazon Elastic Container Service, they for their cluster, maintaining cluster state, they are using this algorithm.
Okay, I'd like to talk about the Paxos algorithm for distributed consensus. So the problem statement is that there is a network of computers, and asynchronously, a client will give a computer some value. Maybe this client gives the computer A the value foo, maybe this client gives the computer D the value bar. And the goal of Paxos is to get all of the computers to accept some value, some value that was given by a client. So maybe they all agree on the value of foo, and computer D has to tell the client, sorry, your value of bar did not get accepted, we all came to consensus on foo. Or maybe just as valid, all the computers come to the consensus on the value of bar, and then computer A has to give the bad news that foo didn't get accepted back to his client. So that's the idea here, and the whole goal of Paxos is to have computers be able to reach consensus when you have no guarantees about the timing of when clients may propose messages, or even how long the communication messages may take in between the computers themselves. So it's kind of a hard, consensus problem, and Paxos addresses it. It's used in a lot of places. It's a cool algorithm, but it is kind of complicated. It was originally written in a paper called The Part-Time Parliament by Leslie Lamport in 1998, and it was about 33 pages long and kind of hard to understand. And so a few years later, Leslie Lamport wrote Paxos Made Simple, which is just 14 pages long, and it's a little bit easier to understand. You can download the paper here, and you can also read about it in the Wikipedia page for Paxos. So here's the relevant pages for our talk today. There's essentially going to be 3 paragraphs, and if you're going to implement Paxos in the safety of your own home, a great way to start is by just taking these 3 paragraphs, pasting them as comments in your code, and just sort of fleshing out the code to blindly obey these three paragraphs, these 2 phases, and sort of this bonus phase down here. So I'm going to describe in this video. I'm going to describe this code here in terms of pictures and flowcharts and stuff. So I'll talk about how the algorithm works, and then show you an example of how it works initially before the network has come to consensus on a value. Then I'll show you an example of what happens when 2 clients propose different values kind of at the same time, like with the foo and the bar, like we saw before. And then I'll show you about what happens if a client proposes a value after the nodes have already all come to consensus on an existing incumbent value. What happens to new values that are proposed? So it works like this. There are 3 sort of flavors of node, 3 flavors of role in this algorithm: proposers, acceptors, and learners. And the proposers, just to start at the beginning, are given some sort of value by some client. Then the proposers would like to reach consensus on some value. And if the
network has not already come to consensus on a value, then the proposer would like to maybe get v default, some default value as the value that is disseminated among the computer network. And it starts this process by issuing a prepare request, a message called a prepare request that has one argument, which is some number n. And essentially this is, for simplicity right now, it's just suppose it's a natural number. It starts at 1 for every proposer, and it's just going to count up from there. And we'll see later how the proposer can essentially append its proposer ID, its unique process identifier to make these all unique natural numbers. But the point is that they have to be in a totally ordered set. So natural numbers are a natural option for this here. So once the proposer sends prepare requests to all of the acceptors, then it just waits. It waits for responses. The acceptors, upon receiving a prepare request, looks to see if the prepare request is new. New in the sense that this n is greater than anything it's seen before, any other prepare request that it's received already. And if that's the case, then the acceptor thinks, aha, this is a new prepare request. I should respond to it. I should pledge allegiance to this proposer, and for the purposes of maybe he'll give me a value that we'll reach consensus on. But I need to tell this proposer if there is already an existing value that the network has already come to consensus on. So that proposer knows that he shouldn't be proposing a new value. He should be getting on board with the existing incumbent value. So those values are captured, are embodied in a so-called proposal data structure, which is just two values, a proposal number. So this n is the same kind of element as this thing here. It comes from a totally ordered set, typically a natural number. And there's also the value here. So this is the value foo or bar or whatever. This does not have to be in a totally ordered set. And this is just it comes from the set of values that people might want to try to disseminate across the network. Okay, that's called the proposal value. So the acceptor responds to a prepare request with a response to prepare request message that contains either the value none, if the acceptor has not already received a proposal, does not already have a proposal that's bouncing around the network, and if the acceptor has accepted a proposal before, and we'll talk about what that means to accept a proposal in a second, then the acceptor clues in the proposer by sending that existing incumbent proposal back to the proposer. So, for example, if the proposer wants to get the value foo everywhere, but the value bar has already been accepted by some acceptor, that acceptor will respond with this proposal that has some number here and the value bar here. Okay, so once a proposer receives a response to the prepare request, it just collects them and sits there waiting for them until it receives responses to the prepare requests from a majority of acceptors. Once it receives responses from a majority of acceptors, then it has the allegiance of the majority of the acceptors, and it gets to propose a value. And what value does it get to propose? Well, v. What value is v? It's either, okay, if there are already existing proposals that the acceptors have gotten on board with, then the proposer has to pick one of those. Which one is it going to pick? Well, it's going to order all of these received proposals by their proposal number and pick the value that corresponds to the greatest proposal. So essentially what this means is I have to pick, as a proposer, I'm going to pick the value corresponding of the greatest, of the most recent proposal that has been bouncing around the network, because that's probably the one that the acceptors have already possibly reached consensus on. Now, if this is an empty set, if there are no received proposals yet, then the proposer thinks, aha, fantastic news. I can pick my v default. Nobody has already heard of any proposals yet. Let me propose one, v default. And what the proposer does in either case, whatever v turns out to be, is it makes a new proposal message with this n and this value. So this is the same number as the prepare request, and the value is whatever this was here. And it sends it out in the form of an accept request. So that's different than a prepare request. An accept request, for one thing, it's blue, not red. And it sends it out to all of the acceptors. Once an acceptor receives an accept request, it knows that the sender, the proposer, has gained a majority support from all of the acceptors, and the acceptor then passes that proposal on to all of the learners, that it knows about, in the form of a decision message. Once a learner receives decision messages from a majority of acceptors, it knows that, hey, these acceptors are all on board with this value. I should really tell the client about this value, and it sets its internal variable value to v, whatever came in the proposal message. So that's the algorithm. Let's go to some examples. Let's talk about.
Okay, due to time constraint, I will stop with that, right? We can go through the video. This link I had given here itself, YouTube link only. You can go through the remaining. Another one is quorum chain algorithm. It's used in the network called quorum, right? And it's used in one variant of the hyperledger also. So here it's called a pluggable that you can add to anything, and it's used in quorum chain. And another one is this Raft and Istanbul BFT combinedly they are used. So here these different nodes can be there, and here also they can be master node, and these some voters can be there, and non-voters also can be there, right? Sorry, not master, maker, and voter, and observer. These three set of nodes are there. So maker is responsible for making the blocks, right? So after making the block, these voters has to respond for that, and they have to vote based on the validity of the block. So the observer will simply receive and validate that block only, right? So after voting, it's observer validate that block, and the recent block with the most vote is taken as the canonical head, or it will be taken into account. It will be added into the chain, blockchain. So it's basically or internally it's using a smart contract. So that's called block voting. The entire consensus mechanism is implemented with the smart contract technique called block voting, right? So like that, number of here also I am listing only few algorithms. So delegated bicentennial fault tolerance also is there. You can go through the links, right? Like that, a number of algorithms are there. Like different implementations, they use different protocol, right? So for a permission blockchain, we have seen this Raft algorithm, practical bicentennial algorithm, federated bicentennial algorithm, and Paxos algorithm, right? Any questions? Okay, if no question, and then we can close the session. I thank you all for your patience listening.
Thank you, ma'am. Thank you so much.